Hi, I'm Javier Flores, and I am from Universitat Politécnica de Catalunya. Today, I will be presenting our paper towards scalable data discovery. This is a joint work with Sergi Nadal and Oscar Romero. So let's start. As we know, organizations are generating so many datasets, and they are following a trend of ingesting data in its native format into a central repository called data lakes. Data lakes have been created to store data that may have value for future insights. The problem is that data lakes contains data generated independently from different sources. So we have data heterogeneity with really different semantics, and with no schema provided. So we don't know exactly what the data lake contains. As a result, we have a data discovery problem to find joinable datasets. Let's consider we have a reference dataset composed by attributes and data instances. And we would like to discover datasets in the data lake that can be crossed by means of common attributes with the reference dataset. This is a complex exploratory task that can be time-consuming. So there are two types of joint relationships that we can discover. First, let's consider DITTR, an attribute from D, and DSITTR, an attribute from DS, a dataset in the data lake. We say these two attributes participate in a syntactic relationship if they share common values. Alternatively, we say that they participate in a semantic relationship if they refer to the same real-world concept. So let's take a look to this kind of attributes. As you can see, in all these attribute pairs, there are some common values that produce a high containment similarity, which is defined as the cardinality of the common values divided by the cardinality of A. But realize that a high containment doesn't necessarily mean it is a relevant join. We have two pairs that don't make sense to be joined since they refer to different concepts, but they have common values. One is referring to one name and the other to some name, while the other pair is about gender and artist name. So these two attribute pairs doesn't make sense to be joined, but yet a high containment. And from all these pairs, we only have one attribute pair that makes sense. It is city name and town name, since they refer to the same concept and share common values. We designed an experiment collecting 188 datasets from open repositories and datasets with different topics to see if containment similarity will be enough to identify semantic joint relationships. So we compute all possible combinations between all the attributes to compute their containment similarity. Here we have a graph with the different thresholds similarity, and we can see that the number of syntactic relationships increase when the threshold for the containment similarity decreases. Although we can see that for thresholds 0.5 and 1, the number of syntactic non-semantic relationships increase. And here we can find cases like the ones commented before, like gender and artist name. Current state of the art falls into this problem and generate too many false positives to filter out manually. So now let's consider we have these tables. First, dataset A about the source located in the north region of Spain. And let's say we are interested to find joinable attributes using the first administration level. We can see that region and product share common values, and they produce a high similarity of 1, but just 1 is relevant to join, and it's the region 1, because they refer to the same concept. So let's take a look at the cardinality proportion, which is the cardinality of A divided by the cardinality of B. We can see that first administration level contains 9 values, and region contains 17 values, while the product contains 1 million distinct values. So we can see that for region, it produces 0.52, which means that it is really close, that the cardinality of first administration level is close to region. But here we can see it is a really low number. It means that it's so different and it's so far away. Here we are talking about 1 million. And in this scenario is very common in data lakes, and the cardinality proportion can provide the information needed to filter syntactic non-semantic relationships that don't make sense and will never add any value. So we define a quality metric based on containment similarity and cardinality proportions. Using the cardinality proportion, we complement the discovery results to identify more semantic pairs of attributes. Then we create 5 quality labels. The higher the quality label, the higher the containment. And the more similar cardinalities they will have. Poor quality is a special case since we only consider the containment bigger or equal than 0.1, and there is no cardinality proportion. Here we will find cases like the 1 million product. So we compare our metric with just containment similarity. Since we have 4 quality labels and 4 containment similarity thresholds, we apply the same threshold for containment to compare them. As we can see, in our metric, the number of non-semantic joint relationships are reduced compared to the containment similarity. An important improvement is that of good and high qualities, which reduce drastically the number of false positives. Our moderate quality also improves, but not as much since 50% are false positives. Nevertheless, moderate and poor quality will be interesting to further explore in some cases with subsequent processing. So the approach is based on data profiling at attribute level, and we'll learn from these profiles whether they are joint candidates or not. Our profiles contain 4 main kinds of metadata. First, we have cardinality referring to distinct values and null values. Value distributions such as the mean and max value, frequent words, octilles. Then we have syntax, which refers to the data type, longest string and shortest string. And finally, we have attribute relationships, which refers to the attributes names distance. Importantly, profiles can be computed once and incrementally maintained. Once we have the profiles, we normalize them, compare them, and use random forest models to predict their joint quality label. We compare our approach with 2 relevant techniques for data discovery: flex matcher, which is based on profiles, but based on a binary class, and LSH ensemble, which is based on locality sensitive caching to estimate the containment similarity. In order to make the comparison, we transfer our output into a binary output, using as label 1 for high and good qualities, and label 0 for non, poor, and moderate qualities. As we can note, NestJDD produces less false positives than LSH ensemble, which produce 50% of false positives. And flex matchers, on the other hand, renders unfeasible at scales due to predictive performance. We want to point out that NestJDD proposes much less false positives, which is a mandatory requirement at scale in order to reduce the time to explore and validate the results. We also measure the scalability of these approaches. We create different test beds based on the considered file sizes. And we measure the pre-runtime, which consists of preparing data for further discoveries, like computing data profiles or creating indexes. For testbed L, LSH ensemble, and flex matcher run out of memory, failing to create the routers for data discovery. For query runtime, LSH ensemble has the best time. This is because at query runtime, they use query through hashings. But if a new dataset appears in the data lake, LSH ensemble requires to recreate the hash index again for all datasets, while for NestJDD, we just need to compute the profile of the new dataset. Finally, we measure our scalability in a distributed environment using CSV in Parquet files by increasing the file size and increasing the number of columns. As bottom line, our approach powered by Spark yields linear scalability, both for number of rows and columns. Further, smart tuning the storage format improves the result. For example, Parquet files provide better times since it benefits from columnar storage. So thanks for listening. To know more, please follow our website or feel free to contact us. Thank you.